Episode 10, CubeSats. You're listening to SPEXcast. Welcome to SPEXcast, a podcast for discussing the science and technology of space exploration. I'm Phil, and joining me today we have TJ.
Hello, everyone.
Auggie.
Hi, everyone.
And Drew.
Hi.
And today we're going to talk about CubeSats. But first, we would just want to plug a little event we're doing. We're doing a live recording of SPEXcast at Imagine RIT on May 7th. If you can't attend, we're taking questions for real astronomers from our audience. So send an email to us at spexcast@gmail.com or tweet your questions at RITSpecs, and we'll ask a real astronomer on the performance stage in front of a live audience, and it'll be pretty sweet.
What is a real astronomer defined as?
Someone who does research with telescopes.
So, and gets paid to do it. Someone who gets paid to perform astronomy.
Yes.
Professional astronomers.
Our guest is Kevin Cook. He's been on a few other podcasts and as a science consultant for the local public radio station for sciencey stuff. He's really cool if you look him up. Our live show topic will be telescopes in astronomy, and we'll talk a little bit about the history, past, present, future, and what RIT's role is in the astronomy scene. But let's get on with the show. Talk about CubeSats. So, first off, who wants to explain what a CubeSat is?
I'll start. So, CubeSats are a kind of picosatellite. They are 10 by 10 by 11.25 centimeters.
Oh, really? They're not 10 by 10 by 10?
They look exactly like cubes, but the mounting system gives them a little bit of extra length in one dimension.
Technical details.
Yes, semantics. So these were invented at Cal Poly San Luis Obispo as a modular system for these kinds of nanosatellites. Before that, different groups, some universities, mostly governments, would be building these small satellites as test platforms. Probably the most famous is Sputnik, the original satellite, about the size of a large beach ball. CubeSats are a lot smaller than that, aided by the miniaturization of electronics. So now you can put all of the major subsystems of a satellite into this little box. And you basically can run one main experiment on these, and they're comparatively a lot cheaper than the usual satellites we launch. CubeSats are hundreds of millions of dollars. Even the small sats are 50 to 100 pounds or millions of dollars. So you're looking at a price anywhere from $75,000 to $150,000 to build one of these.
To build a CubeSat.
Yes.
And that's because the components that go into it, there is a design standard, and there are you can buy off-the-shelf satellite components to plug into your CubeSats and launch them up. And there's a standardized deployment mechanism, right?
Yeah, that's called a P-pod. So
let's explain how a CubeSat gets from if I made a CubeSat and it was done.
Sure.
How do I get it to space?
Sure. So if you wanted to take your CubeSat to space, you would have to get it approved, typically by NASA or whatever launch provider that you were using. So ULA or SpaceX, whatever rocket they had, would approve your payload as a secondary payload. A lot of times they have opportunities for universities to get the launch for free. Other times you could just pay your way in and get a spot on a rocket.
And so a rocket has more capacity, it has more weight that it could lift.
Right.
And instead of just taking the one thing that doesn't use all that mass, they chuck in all these extra little things to get the most into orbit with a single launch.
Sure. So if your rocket is more capable than the mass that you're actually taking, there's space to add secondary payloads, and that essentially is wasted mass. If they don't launch anything or put a mass simulator in there, they're not doing anything with it. So you might as well launch a small satellite like a CubeSat and help another organization out in testing and launching satellites. Yeah. So one of the standards is something called a P-pod, which was developed by Cal Poly. And what that does is essentially they have basically a 3U size where you insert your CubeSat, or say you make a 1U CubeSat. Which
what do you mean by a U is the 10 by 10?
Yeah, so
you can
1U is defined as a 10 by 10 by 10 centimeter cube, and that's basically, if you do the volume calculation, that's a liter. So a 1U is a liter. A 3U would be a 3-liter cube. That'd be 10 by 10 by 30 centimeters.
And if you have 3 of them, like a 3U in the pea pod, it's like 3 peas in
a pod. That's exactly why
pod.
they have that name. Yep. And the acronym stands for something as well.
Drew's smirking at me, but I make sure that pun is clear whenever the pea pod is mentioned.
So anyway, that's a way for them to be ejected. So a lot of the times they'll be launched first to the ISS, and then the ISS will eject them into space, into orbit. And almost every CubeSat ends up in low Earth orbit, or most of the CubeSat that have been launched before.
So when they launch them from the ISS, aren't they worried about it coming back around and like potentially being a threat to impact the space station itself?
So with the P-pod, they actually have a spring inside that'll give them, I think, 1 meter per second of delta V, just a linear push through the P-pod. And so when you're in orbit, a small change of delta V can give you several hundred meters of actual change from the ISS. So they do use P-pods on a lot of rockets and the ISS. One of the most humorous ways I've seen of launching CubeSats is that they'll bring them up with the CRS, Commercial Resupply Service vehicles, Dragon and Cygnus, and then the astronauts will take these and literally kind of throw them out the airlock, which might not be the most high-tech method of deployment, but it works quite well.
So I've heard that mentioned before, but I'm curious, is that just like before the P-pod was developed, they did that? Or is that like a certain specialized payload requires it? Do you know?
So P-pods are really useful for bolting onto rockets, right? So rockets have a lot of extra space. You can throw 1 P-pod, a dozen P-pods on there, and you can fill up that extra capacity. But when you're on the ISS, deployment is a little bit more difficult, right? So just jettisoning things out of the airlock is the easiest method of doing things.
So they don't put a P-pod in the airlock and shoot it out like a bazooka? They actually throw it like a baseball?
I don't believe so. No, it wouldn't be a truck. I'm sure the astronauts try to be gentle with them.
I mean,
but
it's in orbit.
It is a light toss.
It's all you need, right?
So let's talk about CubeSat subsystems.
Okay, so to support a payload in orbit, you need a bunch of different stuff that it relies on to live.
Yeah, one of the big advantages of the CubeSat standard and platform is that it has all of the main subsystems that a real satellite would have. So when universities start building these, you actually get hands-on experience with every subsystem that a real satellite would have, just on a much smaller scale and mostly less complicated. So let's talk about the ADCS, Attitude, Determination, and Control System.
Right. So the attitude is the orientation in space of the satellite or any satellite. And on larger crafts like the space shuttle and the Dragon capsule, for example, they actually have thrusters that shoot out like mini rocket engines that change the orientation. Satellites, and especially cube satellites, have smaller things like reaction wheels, which are spinning masses. And when you have something spinning and you change how fast or slow it spins because of angular momentum, it actually induces a torque on the body, so you can just change the speed of the spinning thing and look to the left. And some other ways you can change your orientation is through a magnetorquer, which is basically an electromagnet that you have a couple of these facing different directions, opposing directions. And when you're floating around in space, you're within Earth's magnetic field. And if you turn on a magnet at a certain power, it'll interact with Earth's magnetic field. And since you're in 0G or microgravity, it'll just slowly bring around your satellite. And people have developed ways of actually taking, like, if an astronaut threw a CubeSat out the airlock and it was tumbling, you could actually there's like a certain way to turn on these magnetorquers and bring it from a tumbling state down to a constant orientation. Yeah. And depending on what you're doing, like if you're doing imaging, for example, ADCS is really, really important. But if you're just using, if you're doing something else like
testing something in microgravity.
Right. And all you need to do is orient your antenna back to Earth. There are antennas that just like point up or down, and you point the downside toward Earth, and that's all you need. So you don't need a lot of precision always. It's really, really dependent on the mission. So that's ADCS in a nutshell.
Yeah. So that was the main control systems. Also, one of the big tasks with ADCS is determining your attitude. So on Earth, we have this nice thing called gravity and also the ground. So we can pretty much assume that the ground is pointing down with respect to the acceleration from gravity. With spacecraft, they are still in the gravity field, but because they're in orbit, there is no down ground to orient against. So you have to basically predefine a orientation that this is up, this is left, this is right, and then you need to determine where the satellite is on all three axes relative to this predetermined coordinate matrix.
I can speak about this a little bit too. I think this is ADCS is the coolest part of the CubeSat for me. If you don't mind, there are two ways to do it. You can add to this if you want, but there's one called the beta angle. It sounds super cool, but it's actually just you know where the sun is. You have solar panels on your thing, and built into the solar panels is a way to detect, how you're oriented relative to the sun. And
so would that be based on just whatever solar panel is getting the most photons, collecting the most photons?
I think so. I think it has to do with the voltage as well. And there might be specific beta angle sensors embedded in each
it's more
solar panel.
It's even more specific than just we're obviously the sun is on this side of the cube because it's collecting the most photons of light. You can actually detect probably at a degree or two how well it's oriented.
I think most of it has to do with the efficiency of the solar panel. Mm-hmm. If you're directly perpendicular to where the sun is, flat on against the sun, it'll be the most efficient for your solar panel to generate power. Mm-hmm. But if you're off angle, it'll be less efficient. You'll make less power. Mm-hmm. And I think if you monitor that, you can tell. Mm-hmm. Another kind of more advanced way to track your position is having a star tracker. And that actually looks at stars in the sky. And the really advanced ones can pick out constellations or known groupings of stars and say, this is exactly where I am. But less advanced star trackers can just say, okay, here's a star. Here's how I'm moving relative to where that star was a second ago. And that's how much I've changed. So I geek out about this stuff, and you guys don't seem as excited as I am.
It's really cool. It's awesome. So with star trackers, it's very basically like a digitalized sextant. So on Earth, we used sextants to determine latitude on the surface of the Earth. And when you're in orbit, you can kind of consider yourself to be moving along a extended sphere of the Earth's surface. So looking at the same stars, you can use the same techniques. We've digitalized it and miniaturized it, but it works just like how ancient sailors determined their position, 300 years ago.
Yeah, if you're not familiar, a sextant is the thing you pointed at, say, the North Star or a star, and you're looking up at an angle, and then you have another thing that points to the horizon, and based on that angle and where you are relative to north or south or whatever, you can tell your latitude and longitude. Right?
Beyond ADCS, some CubeSats even have their own form of propulsion. So a lot of times with chemical propulsion, it's very difficult to get on to as a secondary payload to certain rocket launches. So if the U.S. government is launching $1 billion satellite, they're not necessarily going to want your chemical propulsion, small satellite, putting their $1 billion project at risk.
You mean because it could explode?
Right. Yeah. Because if you put some sort of pressurized chemical or something like that in there, they're worried it may damage the primary payload. But there are CubeSats that have launched with chemical propulsion before, and one of the more interesting forms of propulsion out there is solar sails. So you may have seen this in the news, but Bill Nye's the head of an organization called the Planetary Society, and they launched last year a Kickstarter crowdfunded CubeSat that had a giant solar sail that essentially deployed in low Earth orbit, and it was able to collect light from the sun and actually use that to move it out as a form of propulsion. So basically the photons, even though they have no mass, have a momentum, and they can use that to propel their satellites. And this can be useful for long distance missions because the sun is something that has infinite energy essentially for
our purposes.
For our purposes. Yeah, so you don't need to carry any of your
propellant with it.
propellant. You can just deploy this massive thin filmed solar sail and collect all the light to propel you.
Right, and this even works on a small scale with CubeSats. So Planetary light sail from the Planetary Society was only 3U, so that's only 30 centimeters tall. That's like a foot tall, and it had basically a way thinner version of aluminum foil is what it looked like. It wasn't actually aluminum foil, but and it kind of opened like an umbrella. Is that correct?
Yep. And they had some difficulties, but still the proof of concept, it works. The solar sail works, and they're working on launching another one.
Awesome.
So, yeah.
Is there a subsystem in particular that you like the most, Drew, or know a lot about and geek out about? Like with HAB or
all
things?
of the subsystems have their own unique interest.
Right.
And I think that certainly star trackers are awesome.
Yeah.
So your geeking out about it is warranted. As a mechanical engineering student, my focus, at least in specs in our research organization, is the structure side.
Right.
So it's a standardized form. There are mounting rails that we work around, but it's something that my focus is working with the materials and the geometries that we use to mount everything else that's for the science payload onto the CubeSat.
And how do you go about doing that? Do you use plastic? Do you use like thin aluminum with cutouts?
The mounting rails are aluminum, and for my knowledge fade.
So when you're on orbit, roughly a 1U CubeSat with solar panels on all 6 sides has about 1.2 watts of useful power generation per orbit. And when you start looking,
orbit?
yes, per orbit.
That's like every 45 minutes?
Every 90 minutes.
90 minutes?
Right? So you're spending half of that in darkness, half of that in the sun. And so you either have your constant power draw be under that for your operating system, all your avionics, and then especially when you want to communicate or run power-intensive payloads, then you need to have a full battery system and power management system to supply those power requirements.
So do you mean like to keep it running when you're not in front of the sun, or to spend like 10 orbits gathering energy and charging your batteries so you can use it all at once? Or both?
A little bit of both, right? So you want to have things like your attitude determination system running all the time, right? You want to know exactly where you are and where you're going, where you're changing over time.
Right.
You want all your avionics in like your low power kind of standby state to be running all the time. So those are your baseline power draws. And then when you want to broadcast over radio, that should take a large amount of power for that. And then if you have a payload that needs a lot of power, that's going to need a lot of power for that. So you need to balance your baseline draws every orbit, and then also be able to save up enough power to be able to broadcast information down and run those experiments.
Right. And this is one of the barriers why a lot of CubeSats have really stuck to low Earth orbit, is because as you get farther away from the sun, the energy density of light from the sun gets lower. So like
It's relatively negligible in Earth orbit.
In Earth orbit, it's negligible, but if you like wanted to go past Mars,
Yeah.
Sure, if you want to go far, but
Deep space cube. No, I don't think
a lot of
we've
them
had
have
deep
been
space
low Earth orbit
CubeSats
because that's where
before.
a lot of our rockets are going.
Yeah.
So like we launch satellites, dozens and dozens of them every year, and so a secondary payload that goes with it is just going to end up where that satellite is going.
right?
The
So
rocket's not going any further just to launch that small CubeSat.
and we haven't been sending rockets up specifically for CubeSats. They've only been secondary payloads. Is that correct?
Yes, that's changing. Sherpa is a payload for SpaceX in the coming months, where that's a large number of CubeSats and also small sats, where I think almost 80 different groups are on this carrier. So they developed a bus that stores all these CubeSats through P-pods or special adapters. And then that organization directly deals with the launch provider. And so that's when you spread the cost of a $60-80 million launch among 80 people or 80 entities, then it starts to become affordable.
So what's a small sat? Is that like the big brother of a CubeSat? What is a small sat?
Usually CubeSats or satellites from 100 to 10 kilograms.
Oh, it's just a classification?
Yes.
But the CubeSat's like the specific?
So CubeSats are a standard. I believe they're kind of picosat. They're under 10 kilograms.
I see.
And then small sats are anywhere from 10 to 100 kilograms, I believe.
Are you going to correct them and say they're nanosats and not
No, that's
picosats?
fine.
Fix my
I mean,
prefixes.
so a lot of different sites use different prefixes, so it's not really a big deal. But it's typically nanosats are the 1 to 10 kilogram range, and they have smaller satellites like picosatellites, and
Yes.
there are universities out there. There's a new one just in the news. I can't think of the name off the top of my head right now. That's coming up with a super tiny satellite, kind of like what we talked about in the last episode that Stephen Hawking wants to send all the way to Alpha
Yeah.
Centauri, like even smaller than a CubeSat, and that's more like the picosat, 0.1 to 1 kilogram range.
Right. So for the next subsystem that's really important for CubeSats, you want to talk about avionics a little bit?
Sure, we can talk about avionics. So avionics is very important because that is the logic that runs all of the commands of the satellite.
The motherboard, right?
Yeah, it's the motherboard, the main processor, and
brain,
the
yeah.
data bus that connects all the different subsystems together. So we talked about ADCS and how important it is to determine where you're pointing. So there is the specific hardware dedicated to that. So the star trackers, and whatever you're using to change your orientation. But all of the logic that runs through that has to run on the avionics equipment. And so we talked about detumbling and how that's very important. When you deploy from a P-pod, usually you're going to be in a tumble. And you need to be able to stop that tumbling motion, be stable, deploy your antennas, and start communicating with the ground.
Right.
All of that code, which is very complicated code, very complicated algorithms to do that efficiently, has to run on the avionics board.
And that it has to be done. It's not remote control because
That all has to be removed, especially for that, because you're not going to be able to communicate.
right when it's jettisoned from the P-pod, it's not like we're talking to it the whole way through. It's on its own, and it says, "Okay, I'm on. I've got to detumble now," and do that all by itself. And so that's pre-programmed into the avionics.
Yeah, so like you'll have
Package.
that. Yeah, it's running off the avionics main board and using all your ADCS sensors and impulse methods.
So is there only one board? I don't know what to call it. What do you call it?
I would say it's
PCB?
called the main board. So there are lots of different PCBs. Most of the components in the CubeSat are going to be microelectronics mounted to PCBs. But there's
PCB
usually
being the
circuit boards.
what does the P stand for?
Printed circuit.
Oh, okay.
Yes.
Sorry.
So if you look at the internal structure of a CubeSat, right, it's on the outside it's a big cube. Inside it's actually a bunch of PCBs stacked on top of each other, and usually they'll have one main data bus going up a side. So you have all these different layers mounted to the internal rails.
It's kind of like if I have my motherboard in my tower and a bunch of graphics cards like stacked up, plugged into it on the side.
So not exactly. So a motherboard, if people are familiar with building computers, you have a large flat PCB, and
Yeah.
then you have vertical PCBs sticking out.
Yeah, that's for a regular desktop computer.
For this, all the PCBs are stacked directly on top of each other. They're all 10 by 10 squares stacked on top of
Physically
each other.
connected to each other.
And you'll have one main bus that runs up either one side or both sides.
Okay.
And so that's how each board communicates to every other board, is through that bus on the
okay.
side. Right? Because you can't have...
So they're just pins that connect, like when you stack them on top of each other, it's just like a row of pins on one side.
Yeah, exactly.
Oh,
and if you
okay.
need more connections, you can do on two sides. I haven't seen any designs that use 3 or more for data connections, but that's usually how it goes.
Okay.
And so when you're looking at 1.2 watts of power per orbit, that means that if you want to have useful power for transmitting radio and running your payload and things like that, your constant power draw that your avionics runs on has to be a lot lower. I can look at the actual numbers that we calculated for our satellite, but you're looking at microcontrollers. You're not going to be running, advanced
Yeah.
like x86 processors. You're looking at microcontrollers, and you really can't do multiple.
So
of
like
those.
something that would be in a lower end cell phone?
So there have been CubeSats that used they're called Phonesats that use ARM processors.
But even lower than that?
What we're looking at is even
generally speaking?
we're looking at microcontrollers. So
Yeah, so the phone industry has just taken off with the iPhone and everything like that. And so NASA started the project, the Phonesat project, which was essentially in 2009, they launched a Nexus 1, and they used, they had lithium batteries there, but they used basically all the components that were already built into the Nexus 1 smartphone. And the whole thing to build only cost $3,500 to construct an entire CubeSat, which is insanely cheap for a CubeSat. And they've just kind of been expanding on that. There's been, I think, 3 now that have launched. They'll throw in like an S-band radio to help with the avionics, but it's essentially just launching a cell phone, taking advantage of, the GPS receiver and transmitter that's already in the cell phone, the processor, because kind of the advancements that companies like Apple and Samsung have made in these small microprocessors have really just enabled a whole new, possibilities for CubeSats.
But generally speaking, do those require too much power? Like TJ, you said that usually we don't use something. We use something.
We would use an 86-bit like for your computer, but some of these newer like smartphones, your smartphone does not drain that much power. It's crucial for them because as they get thinner and thinner to use less energy. Right. So if you look at your smartphone, that has a 12-hour battery life roughly, and it can fit in your hand, so it's small enough to fit into CubeSat. You know what I mean?
Right. So when TJ, you were talking about a different thing other than ARM processors, which are like mostly Android and iPhone processors. What you said there was a distinction. I'm curious, what is the distinction between what you were talking about and what Augie's talking about?
So I was talking about microcontrollers.
Yeah,
so
what's the difference between a microcontroller and
they're
like
less complete processors. So the instruction set you can run on a microprocessor versus an ARM processor or an x86 chip is different and more limited.
So it's like the microcontroller doesn't have an operating system where a microprocessor would have an operating system?
No, so you'd still run an operating system, and CubeSats run real-time operating systems, which are a little different style than what's Windows. But they're limited instruction sets, so they're less versatile.
Okay.
Is that a problem with CubeSats?
No. So you do a lot of different things.
You do.
I'm trying to look up the actual power requirements we had for our first CubeSat design. But
CubeSats are designed for, it's like a one-track mind. You go there to do one thing. So yes, you have to detumble. Yes, you have to manage all these things, but
yes, but I'm almost with what Drew I think is leaning at, and I kind of think it is maybe not a problem, but it's something that could be changed because we've gotten to the point where we can develop such small processors. Like your iPhone costs less than $650. So if you take the processor out of that, and it is capable of doing many different things, because it is so cheap, it doesn't matter. As long as you can program something or come up with some sort of standard that utilizes the same platforms that your phone does, then you take advantage of the rest of the industry and capitalism and commercialization driving the cost down. So that I think may be the next leap that CubeSats need to take to go from the current $100,000 range to maybe drop it down to $10,000. And they may even be even more capable. It's just you still have to worry about transmitting data. So when you
bring that up,
so you don't want to transmit any excessive data. So your processor, if it's capable of running more processes in space, that should be fine. But when you transmit that back to Earth, there's not great communication systems set up for that. So
can we talk a little bit about the communications? That's the next subsystem I wanted to talk about. So CubeSat can do all this crazy stuff in space. But then to talk to Earth or to receive commands from Earth, they usually use radio bands, right? You have to get approval from the U.S. government and whatever, make sure you're not accidentally using military frequencies. Is that how it works? TJ, have you done this before?
Yeah, so we actually, in our astrodynamics special topics course, went into a lot of the communications and how radio communications work on a theoretical level and on a practical level for a CubeSat. So one of the big issues is that it's power, right? So from the ground, you can basically have unlimited power for transmitting, and you can build large antennas for receiving.
Large antennas being for weaker signals?
Yes. So basically, you have a signal to noise ratio, and you need the incoming signal is for receiving data from the satellite is based on the power you send to the antenna. Also, antenna design can also increase what's called the gain of the transmitter. And on the ground, the size and design of the antenna can increase the gain of the receiving antenna. And so what you want to do is that with limited power, you need to send useful data back, and you need to have a signal-to-noise ratio where you can encode digitally ones and zeros. And then that basically determines your bandwidth.
So yeah, when you're planning comms, you also have to consider like being smart about which data you send, because you have a very limited budget, how often you send data, and which bands of the radio frequencies you use.
Yeah, so it's more of effect of power and distance.
Are certain frequencies more efficient?
Yes.
It's a very tentative yes.
There's lots and lots of different factors that go into this.
Okay.
Basically, like antenna size increases. I could bust out the notes
That's
and
fine.
Go over it, but I really can't do this.
Speaking of antennas, we're talking about a really small satellite. How would CubeSats manage the antennas? Like, do you just have a telescoping one, or
Most use actually measuring tape. So they have an omnidirectional antenna that's just built with measuring tape that just will extend out. Right?
So since measuring tape is metal, right, and it's a straight line, and if you've ever played with measuring tape before and you kind of like feed it out, you can tell that it stays straight, or it likes to stay straight. You can just shoot out, or what do they do? Like preload the measuring tape and then release it
On a spring, I think
They
so,
take
yeah.
actual measuring tapes and put them in.
right, and you just
And then you
extend
just
it.
run power to the measuring tape.
Right, so since like if you
It's really scary how simple it is.
I mean, you could probably do this on Earth if you took
without a doubt.
CB radio or something and just had a really long measuring tape. There you go. That's an antenna.
Yeah, so your antenna needs to be a conductive material, and so a metallic measuring tape of the right length and weight. You want to make sure it doesn't have to be very long, so you can save mass on there. And so usually you can put 4, I think. Usually put 1 in each corner, and then you'll have 4 omnidirectional antennas.
Right, so that means no matter what orientation CubeSat is in, it will always be transmitting data. Some of the data will get to Earth. Doesn't matter which antenna it goes out from. Do you think it would be more expensive power-wise to reorient the craft toward Earth and then transmit with only 1 antenna rather than carrying 4 or transmitting through 4 at once? Is there a difference in the power margins there? I wonder. You might not be able to answer this.
No, I have no evidence of this, but I think that the reason that the standard is to use 4 is because it's not cheaper in terms of power to reorient yourself to transmit and then transmit. If we can transmit and be tumbling, then that saves us the power to orient ourselves, which can be, and if we're using magnetorquers, involves using power to
It's cheaper
orient
to
with-
send out of 4 antennas than it is to try to reorient yourself.
potentially.
It's more of a
And redundancy thing too. Redundancy.
Yeah, it's more of a
Everyone
cost-benefit analysis and a risk assessment where if you can't communicate to and from the satellite, that's mission. The
it's a
mission's
dead
over,
satellite.
right? And so while it might not be as efficient to have those antennas, it's more important to know that when you send a communication, a command to your satellite, that it's going to receive it and attempt to fill it out. And so that's really something you have to balance, because you can make each subsystem as efficient as possible, but you might introduce more risk and actually harm the overall mission.
Right. And speaking of dead satellites, one thing I wanted to mention is that when a university or a company or whatever makes a satellite and asks NASA to launch it for them, there's a requirement that it deorbits after 25 years or something, right?
Actually, they prefer it to deorbit within 10 years. And you can get, actually, they really want it to deorbit as soon as possible.
No matter
to
what,
reduce the amount
whether
of space jump. But if you have a mission that for some reason needs to be up there for a long period of time, then you can get around it. But most of the time, nobody's developing a CubeSat that's designed to last 10 years
Right,
in transmit.
even if the satellite dies, it's like kind of built into the mission plan to deorbit without additional input, right? And that's to cut down on space debris. Like if anyone's seen Gravity, let's hope that wasn't a CubeSat. I haven't seen the movie myself, but
Yeah, so essentially it will just deorbit, and a lot of times CubeSats will deploy whatever they already have to increase their surface area, so they pick up more atmospheric drag, and it's atmospheric drag that actually brings them down over time. So a lot of bigger satellites, more expensive, more important satellites, like for example the ISS, actually have thrusters that will keep it at the altitude that prevent it from falling back and deorbiting. So you have to keep refueling that.
even when you're way up there, there's still a thin amount of atmosphere.
Yep.
And then over years and years, it's like drag here on Earth, but just like dialed down way back.
Exactly, yeah.
Yeah. So, yeah, atmospheric drag for low Earth orbit satellites is definitely a consideration with the ISS at roughly 300 kilometers, I believe. They have to do reboost because they have lots and lots of surface area, which is one of the main components for orbital drag. And they do have relatively high mass for most of that, which lets them stay up a while. Now, with a CubeSat, you're not in a very aerodynamic shape, and you don't have a lot of momentum stored in there, and so you're going to deorbit relatively quickly.
Right, and when after, there's a lot of drag on it, pulling and pulling and pulling, years at a time, it gets to a point where it can't orbit anymore, falls through the denser parts of the atmosphere super fast because it's orbital speeds, and burns up like a meteorite.
Now that's for satellites in general, but for CubeSats, I believe they deorbit in a few months.
So like a lot of CubeSats will deorbit in under a year. Other times they stay. Some are still up there that launched 10 years ago. So it all depends on at what point you release the CubeSat.
And is that defined by the mission plans, or is that defined just like
Oftentimes
variations?
It's defined by the mission plans, yeah. So you know what orbit you're going to be released at, but sometimes rockets have a window where they want to release their payload.
Right.
And they might release it at a higher payload or a higher orbit or a lower one, and based on that, your CubeSat could be up there for an extra 2 years, just depending on a few extra meters essentially.
And if it doesn't matter for your mission, then you don't really care.
Right.
But if you have something like you said where you wanted to be up there for 10 years, you obviously wouldn't go on that mission.
Yeah. So with CubeSats, usually most of the experiments are within 6 months to a year is their lifetime.
And does that include, how long does it take to begin an experiment after you launch out of a peapod?
So with NASA's restrictions, you think you have to do 30 minutes before you can boot up, and then depending on what your payload plan, mission plan is.
So the soonest you can start is 30 minutes after it's launched
deployed.
out of the peapod.
Yeah. But it just depends on what your experiment is. If you're collecting data for a couple months, then you need to be up there for 3 to 6 months. But if you're just doing a deployment test, then you deploy, you get enough power from your solar panels, everything's ready, you communicate, and then you deploy, and success failure right there. But yeah, they're really not going to last a year, 5 years, 10 years. Satellite providers have a really hard time designing equipment for communication satellites that last 10, 15 years because they're kind of in a race where it's so expensive to put a satellite up that you want it to last as long as possible. And then in order to make it as long as possible, it has to be more and more expensive. And so the whole idea with CubeSats is to be cheap, one-off experiments. They're not supposed to be, long-term data gathering resources because it's cheaper to build another one. So
Right.
if you need, constant data set for 2 years, you can launch 4 CubeSats for $400,000 instead of designing a small sat, which might be $2 million that will last 5 years.
And all the data is transmitted in orbit, so we don't care that it burns up in the atmosphere after a few months anyways. We're not trying to recover it.
Right. This is a very good point, because one of the payloads that we're pursuing in SPECs is radiation memory testing. Now, this could be done on Earth. There are radiation test chambers, a very few radiation test chambers throughout the country and throughout the world, but it's cheaper because there are so many people who need time on these chambers and the cost with getting time on this chamber, that it's cheaper for us to put our various forms of memory
Computer
on a
memory,
CubeSat
like RAM.
and send it up.
It's not like matching card games, testing my memory.
No, yeah,
Memory
so like,
test.
one of our
Sorry.
payloads that kind of ties into avionics is that, you have your processors, but you also need to store your operating system and whatever data you have on orbit. And in low Earth orbit, you're in a very high radiation environment, so you're getting cosmic rays, alpha, beta, gamma particles, whole gamut. And with silicon chips, the micro components that we use, they don't like to be bombarded by radiation, turns out. And so you have to use unique materials. Germanium chips are really common, and design things to be radiation tolerant to actually be able to use all this great, microelectronic technology that we use every day. So one of our missions is to test physically different memory cells in space. So basically having one main board with 4, identically sized chips by die size and memory size, and then writing the same information to each, and then waiting a amount of time for radiation to interact with the chips, and then reading back from that. And you can actually see with that relatively simple experiment which kinds of memory are most resistant and least resistant,
And
etc.
actually quantify that performance.
Yeah, and so like we can introduce radiation on the ground of all the different types, but at the end of the day, these chips on a larger satellite need to operate in space. And so being able to test just that one component in space and get the exact same radiation profile and intensities, we can validate that. And so someone else who's launching, their $1 million satellite or $10 million satellite can be somewhat confident that they know how these chips are going to work.
Cool. And you'll have a demonstration of some sort of this and like a poster of your mission plan and everything at Imagine RIT for those of us who are in Rochester on May 7th. That's all I've got for this episode. Anything to add, Drew?
Well, we could talk about what else Specs is doing in terms of CubeSats.
Sure.
So we're looking to participate in one of the launch initiatives. I'm not sure which.
The CubeSat launch initiative held by NASA with a due date in the 3rd week of November.
Crunch time already.
Yes. So we're pursuing 2 primary CubeSats. The one that we already discussed, the radiation memory testing, and the other one is a electrodynamic tether, where we use essentially a long measuring tape, so a long antenna, to interact. We send current through this, and we interact with the Earth's magnetic field to gain energy for use in the CubeSat by deorbiting. So we essentially convert our kinetic energy into potential and electric energy.
So basically,
potential energy is
you
your
have a
height.
conductive wire moving through an electric magnetic field, and that's
Oh, and
going to
that'll
induce
generate
a
it.
current in the wire, and then you can basically harvest electricity through that. And so that does create a magnetic force on the wire that's going to slow you down. So you're going to lose kinetic energy. You're going to lose total orbital energy. So over time, you're going to lose height and speed. But that is one way of generating power for low Earth orbit satellites.
Yeah, it's an alternative to, if for short burst energies, an alternative to solar or,
I would guess chemical.
chemical, but I don't think we can send preloaded chemical up, can we?
Like batteries.
Fuel cells are big and heavy. Don't use fuel cells in a CubeSat.
Yeah.
So like I mentioned earlier, you don't want to have any danger to your primary satellite when you fly these things. But we also have a third payload, which is affiliated with SPEX, but that my senior design group has been working on, and that essentially looks at how proteins fold in space. And what it does is it uses a UV LED and measures the fluorescence of certain proteins after we mix them with reagents. So we're going to have a breadboard prototype for that with our whole assay set up at Imagine RIT on the 7th. Cool.
All right, that wraps up our discussion about CubeSats and all the fun stuff that they do. Thanks for listening. We'll be back with another discussion on space exploration, science, and technology in about a week. And if you would like to share your thoughts on this topic, or if you have requests for another one, send your requests to SPEXcast@gmail.com or tweet to us at RITSpecs. And also, don't forget to send in your questions for us to ask real-life astronomers anything you might be wondering, or something fun. This podcast has been made possible by RIT Specs, a space exploration student faculty research organization at the Rochester Institute of Technology. Special thanks to the Interactive Learning Grant Program for giving us the tools to promote student and faculty engagement outside the classroom. Our music is by Kevin Hartnell. This has been SPEXcast. We'll see you next week.